In this video, we introduced the thin film interference of light, and we learned how to relate the thickness of a thin film to the wavelengths of light which interfere constructively and destructively when the light reflects off of the film. On the left, we have a couple pictures of thin film interference that I took this morning. Both of these used bicycle lubricant sprayed onto water. In the top picture, I put a couple drops of triflow lubricant on some water in a dish, and I got some nice thin film interference out of that. In the second picture, I had drained the water off of the dish, so it's like triflow and a little bit of water on this ceramic dish, and we get all these wonderful colors popping out in the sunlight. Note that the color magenta is common in thin film interference, and it's not a color you see very often in nature. When you do see magenta, it's usually a thin film interference situation. Whether it's a film of oil on water, interference in the thin layers of material in a bird's feather, or the interference colors in an insect's wing. These are called structural colors because it's not chemistry. There are no pigments involved, just reflections happening through thin films. And these reflections are going to cause constructive and destructive interference of different wavelengths of light, producing a pretty cool light show. In order to figure out thin film interference, we have to incorporate some basic facts from previous videos, and I'll post links to those videos as we go. First, when light transitions from one medium to the next, the wavelength changes. If the wavelength in vacuum is lambda, then the wavelength in a material with index of refraction n is given by lambda over n. And we normally notate that as lambda prime. So whenever you're dealing with light inside a material, don't forget to change your wavelength to the wavelength of that light in that material with a particular index of refraction. Second, when light reflects at a slow to fast transition, in other words, an interface where the index of refraction decreases, the reflected wave is not going to be phase shifted. Third, when light reflects at a fast to slow transition, in other words, the index of refraction is increasing when we switch materials, the reflected wave is phase shifted by a half a wavelength or 180 degrees. So there are two basic cases we cover with thin film interference, and the first one we're going to talk about is the fast to slow to fast case. What I mean by fast, slow, fast, if I look at my diagram, is that I have light coming in with an index of refraction of 1, that's in the air, and then it hits this layer that has an index of refraction of 1.5. That's the fast to slow transition. Then when the light gets all the way to the next interface, the index of refraction decreases down to 1.33, so I have a slow to fast transition. Remember, this matters because when light transitions from fast to slow, it experiences a phase shift, but when it transitions from slow to fast, it doesn't experience a phase shift. So the classic example of a fast to slow to fast thin film situation is a thin layer of oil floating on water. So we've all seen this if it hasn't rained for a while. If you look at the puddles in a parking lot, you'll see thin film interference happening from motor oil floating on the surface of those puddles. So that's what's set up in this diagram. I have a thin film of oil, index of refraction 1.5, sitting on water that's an index of refraction of about 1.33, and the air above that is very approximately equal to 1, so we're going to call that exactly 1 for the index of refraction of air. For simplicity, we're taking an incident light ray that's perpendicular to the surface of the oil. That light ray reflects off of the air-oil interface, and that's the first reflection I've shown here. But the light also penetrates through the oil and then reflects off of the oil-water interface, and that's the reflection I've shown here. Because the first reflection happens at a fast to slow interface, that's phase shifted. I'll just write PS for that. But the second reflection happens at a slow to fast interface, that's not phase shifted, so no PS. So in the first diagram, I've already given away that this is going to cause destructive interference between the two reflected rays, and we're trying to figure out why. And I've labeled over here the thickness of the oil film as being lambda prime over 2, so the wavelength of the light in the oil over 2. Why should this cause destructive interference? So again, the first reflection off of the oil, that's a phase shifted reflection. My second reflection is not phase shifted, but it also has to travel a farther distance. It has to go through the oil to the water and all the way back. In other words, it covers 2 thicknesses worth of extra travel distance. Extra travel distance can cause a phase shift. So the extra travel distance is twice the thickness of that oil layer, but that's going to be equal to exactly 1 wavelength of the light. So when that reflection emerges, it hasn't been phase shifted because of the reflection off of the water. It hasn't been phase shifted because of the extra travel distance, because the extra travel distance was equal to exactly one wavelength. So this reflection emerges with no phase shift at all, and it's coming out of the same place as a phase shifted reflection off of the air to oil interface. So the two waves get 180 degrees out of phase, and they're going to interfere destructively. Now we can generalize this because any thickness that gives us an integer number of wavelengths of extra travel distance, that 2t, is going to create the same destructive interference. So anytime that 2t is equal to n lambda prime, where n is 1, 2, 3, and so on, for a fast to slow to fast thin film situation, you're going to get destructive interference. Let's go ahead and apply this to an example. So we're told for a film of oil with index 1.5 on water with index 1.33, calculate the two thinnest layers of oil that will give destructive interference when yellow 585 nanometer light strikes the layer at right angles. So the first step in these problems every time it's so easy to forget. But remember the wavelength of that light. It might be 585 nanometers in air, but it's not going to be anymore once it's in the oil. The wavelength actually decreases. That's lambda prime, and that's what we're going to start with. So the new wavelength is just the wavelength in vacuum or in air to a good approximation, divided by the index of refraction. So this light has a wavelength of 390 nanometers in the oil. Again, destructive interference is going to happen when the extra travel distance, that's twice the thickness of the layer, is equal to an integer number of wavelengths within that layer. So our thinnest layer of oil happens with the n equals 1 case. So I could say 2 times T1 is equal to lambda prime. The next thickest layer of oil that causes destructive interference of this wavelength, that's T2, and I know that 2T2 is going to be 2 lambda prime, just subbing in n equals 2. Solving for T1, that's lambda prime, the wavelength in the oil, over 2, and I get 195 nanometers for the thickness. Solving for T2, that's just equal to lambda prime, and that's 390 nanometers. So note what happens when we have white light incident on these oil layers. If you destructively interfere the yellow 585 nanometer light out of that white mixture, it's going to be missing from the reflection, but the other wavelengths of light will still be there. Now there's a rather wide neighborhood of that yellow light where the destructive interference is partial. So basically what this does is it carves out the middle of the visible spectrum. Yellow's in the middle of the visible spectrum. This leaves violet and red primarily in the reflection. When you combine violet and red, you get magenta. So recall what our oil slick looked like. There's repeated stripes of different colors, but you can see multiple locations where there's a magenta stripe. In each of those locations, the thickness of the film is right to give you destructive interference around the middle of the visible spectrum. And notice there are many, many different thicknesses that can cause this to occur. All right, let's move on to the second picture. So this is the case of constructive interference. And again, I started with a specific thickness to make a point, and then we're going to generalize after that. So in this case, my incident light is hitting a layer of oil that has a thickness of 1/4 of a wavelength of the light within the oil. That 1/4 of a wavelength creates an extra travel distance for the ray that reflects off the oil-water interface of twice the thickness, which is lambda prime, over 2. Now that extra travel distance does cause a phase shift because it's only half a wavelength of extra travel distance. So remember the first reflection, that one had a phase shift because it was a fast to slow transition. My second reflection, that also has a phase shift, not because it was a fast to slow transition. The surface it reflects off was going from slow to fast, but because I have this extra travel distance of 1/2 of a wavelength. So because both of those reflections are phase shifted by 180 degrees or a half wavelength, they're going to be aligned with each other and interfere constructively when they come out of the material. To generalize the formula, what I need is a thickness so that 2 times the thickness gives me a half wavelength of extra travel distance plus possibly an integer number of additional wavelengths. All that matters is I get offset by that 1/2. So the generalization is like this. I need to get a half wavelength plus possibly an integer number of additional wavelengths. That's going to cause the net phase shift of that second reflected ray. Cleaning this up a little bit, I get n plus a half times lambda prime. And the thinnest layer that was giving us constructive interference is the first one that we found, where 2 times the thickness gives me exactly 1/2 wavelength of extra travel distance. That corresponds to n equals 0. So this formula starts at n equals 0, and then 1, 2, and so on. Now in our second example, we're asked to calculate the thinnest layer of oil causing 585 nanometer light to interfere constructively. So that's where twice the thickness of the layer gives me an additional half wavelength of travel distance. So 2t is equal to lambda prime over 2. Solving for t, and I've already got lambda prime from the first example, that's 390 nanometers. So I get 390 over 4. This gives me a thickness of 97.5 nanometers. So at that thickness, the yellow light interferes constructively. My suspicion is that's where you see a yellow stripe in the thin film pattern for an oil slick. So going back to our picture, we have a nice yellow stripe right here. I can't think of a way to obtain yellow from destructive interference, so I suspect those yellow stripes are caused by the constructive interference. There are also greens and purples that are prominent, and I don't know if those are caused by destructive or constructive interferences. The one that's always been clearest to me is to talk about that magenta, because I know what that is. That's yellow missing from the visible spectrum. The next major case that we cover is the fast to slower case. And the actual materials that I'm using in this diagram is a coating of fluorite on a crown glass lens. So this is a common way of creating an anti-reflective coating on a camera lens, for example. I can see my index of refraction just keeps getting bigger. So the fluorite is like 1.434 and the crown glass is 1.52. So this means my first reflected ray is going to be phase shifted because the light is slowing down. I get a phase shift in the reflection. The second one experiences a phase shift at its reflection as well. But then I have to consider what happens due to the extra travel distance within the material. Now I've set this up so the thickness of the fluorite coating is a 1/4 wavelength for the light within fluorite. The extra travel distance for that wave is going to be twice the thickness, so that's lambda prime over 2. Well, that produces a phase shift due to the extra travel distance. So this second ray is phase shifted by a half wavelength once because of the reflection, and a second time because of the extra travel distance. So it comes out of the material with no phase shift. These are now out of phase with each other and they interfere destructively. To generalize this result, I could tack on an integer number of extra wavelengths within this extra travel distance of 2t, and it will still arrive with no phase shift and interfere destructively with the first reflection. So we arrive at our general formula for destructive interference in the fast, slower case. Again, this one starts with n equals 0. In our example, we're told the anti-reflective coating for a camera lens has a thin film of fluorite applied to crown glass, and we want the required thickness so the film causes 585 nanometer yellow light to interfere destructively. Well, there are many thicknesses that could get this done, so I suppose the one we're interested in is the minimum required thickness so the film causes this destructive interference. So that's the n equals 0 case in our formula. It looks just like the picture all the way on the left. Twice the thickness is lambda prime over 2. In other words, the thickness is lambda prime over 4. Again, we have to compute what's the wavelength of the light within the fluorite coating before we can get this done. So 585 nanometers divided by 1.434 for the index of refraction. Into 3 sig figs, I get 408 nanometers for the wavelength of the light. So I can plug in and find my minimum thickness, 408 nanometers over 4, which gives me a thickness of 102 nanometers for this anti-reflective coating. Again, we're talking about yellow light interfering destructively. And if white light is incident on this camera lens, the reflection is going to be missing the middle part of the visible spectrum. And you may have noticed this with camera lenses before, but they have a weird magenta hue to them. Again, that's because the reflection has mostly violet and red in it. The combination of violet and red is magenta. All right, finally, we're going to cover constructive interference in the fast, slow, slower case. And I've already kind of given away that it should happen if the thickness of my thin film is lambda prime over 2. So let's try to figure it out. Again, the first reflection is phase shifted because that's a fast to slow transition. What about my second reflection? That's phase shifted at the interface of the fluorite and the crown glass because it's a fast to slow transition as well. Then I made the thickness of the coating equal to half a wavelength, which means the extra travel distance for that wave, that's twice the thickness, is exactly 1 wavelength. Well, an extra wavelength of travel distance doesn't shift the phase at all. So this reflection also emerges from the material, phase shifted once. That puts both reflections back in phase, and they're going to interfere constructively. To generalize this, as long as I have an integer number of wavelengths for my extra travel distance 2t, I'm going to get constructive interference. And again, in my example, I should have said minimum. Find the minimum thickness of a film that would cause 585 nanometer light to interfere constructively. So that's the n equals 1 case in our formula, and I have 2t is equal to lambda prime. Again, that's the same as saying t is equal to lambda prime over 2. And I already have lambda prime. That was 408 nanometers. So I get a thickness of 204 nanometers, causing constructive interference. We're going to wrap things up with what I like to call ultra-thin films. I don't know if that's a very popular thing to call them, but that's what I call them. And a common place to see an ultra-thin film is in the wall of a bubble or around the edges of an oil slick. These are both fast to slow to fast transitions, so that's the case we're going to talk about here. So for the case of the wall of a bubble, I said the index of refraction is 1.33, so about the same as water. It's water with soap in it, but it's basically water. And I have a very thin wall on this bubble, and I'm saying the thickness is much less than the wavelength of light that's incident on it. So just to put a number on it, you could imagine we're talking about visible light here. So what if I made the thickness like 20 nanometers? The shortest wavelength of visible light is like 400 nanometers. So we're talking a very small fraction of the wavelength of the light. So my first reflected ray off of this bubble wall is going to be phase shifted because it's a fast to slow transition. My second reflected ray is not phase shifted at the reflection because it's a slow to fast transition. On top of that, the extra travel distance for that ray, in other words, twice the thickness, is pretty much negligible. It's not a significant percentage of a wavelength for the light. So there's no phase shift caused by the reflection. There's no phase shift caused by the extra travel distance. So these two reflected rays are going to interfere destructively with each other. The interesting thing about this is that we didn't even have to mention what the wavelength was. It could be 400 nanometer violet light or 700 nanometer red light. The same thing is going to be true. The first reflection is phase shifted, the second reflection is not phase shifted, and the reflections interfere destructively. In other words, every wavelength of light interferes destructively if the thickness of a film becomes negligible compared to the wavelength of the light. To illustrate this, I got this photograph this morning of a bubble. So this is just wire bent into a loop. I made some bubble solution using dish soap and glycerin and water. And I put this in front of a black background so I didn't have to worry about any light coming through the backside of the bubble. And behind where I'm holding the camera, there's a bright light on the wall. The first thing I notice is that I have all of these lovely stripes. I have magentas, yellows and oranges and greens. And these patterns are repeating. And the reason why is that the bubble is actually thicker at the bottom. So gravity pulls that film down as you hold the bubble vertically in place. And the film is just getting thicker and thicker and thicker as I go lower. So we're repeatedly seeing that magenta line, for example, where I get destructive interference on yellow light. And we're repeatedly seeing the yellow line. So this is just hitting all those different values of n in the formulas that we derived. The ultra-thin film interference comes in at the top of the bubble. So this was actually the last picture I got. I took about half a dozen really fast, and this is the last one I got right before the bubble popped. What you see right before it pops is in this region, nothing but black, no reflection coming off of it, because reflections of every wavelength of light are interfering destructively with each other. The same phenomenon leads to the black appearance around the edge of an oil slick where the thickness of the film drops well below 400 nanometers. And that ultra-thin film interference is actually used as a way of mapping oil spills on the ocean. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.